Hello everyone, this is BB Ramat. Today I am going to discuss the next part of the current electricity, that is limitations of Ohm's law. We learned the concept of Ohm's law. Today we are going to discuss limitations of Ohm's law, in which the first limitation is Ohm's law holds good only for metallic conductors at a moderate temperature. See, according to this, at moderate temperature, the Ohm's law holds good only for metallic conductors. This is the first limitation. Then second limitation, at very low and at very high temperature, even metallic conductors do not obey the Ohm's law. See, so according to this, at very low and at a very high temperature, even metallic conductors do not obey the Ohm's law. Because in the definition, so we learned the concept of Ohm's law. According to definition, the current through the conductor is directly proportional to potential difference across the ends of the conductor. The temperature and other physical conditions remains constant. According to definition, the temperature should constant. So at very low temperature and very high temperature, even metallic conductors do not obey the Ohm's law. The next thing is next limitation is this law is not obeyed by vacuum tubes, discharge tubes, semiconductors, and electrolytes. See, the next limitation is like this: Ohm's law does not obey by the vacuum tubes, discharge tubes, semiconductors, and electrolytes. See, so there are some diagrams are here, which is given as in the figure. So, however, actually materials such as semiconductors, ionic conductors, and electrolytes and plasma like this, the IV graph is non-linear. See, so in the following graphs which shows IV characteristics, IV nothing but the current along one axis and voltage along another axis, that gives the IV characteristics. So in the IV characteristics, the semiconductors, electrolytic cells, plasma, and ionic conductors, these shows non-linear graph as shown in the figure. In these materials and the devices using these materials, the proportionality of V and I does not holds good. See, in the first diagram here, there are two curves are here. One is a straight line, that is a dotted line. Another one is a curved line. So the curved line which does not obey the Ohm's law. If that is according to first one, the Ohm's law holds good only for metallic conductors at moderate temperature. At constant temperature, this Ohm's law, the dotted line that shows the Ohm's law holds good. So according to this, the current and voltages are directly proportional to each other. Then so the second curve, that is the curve, that is a continuous curve is given here. So this continuous curve shows so the non-linear graph. Then the device which does not obey Ohm's law are called as nanomic devices. In a certain devices, I is not proportional to V beyond the certain stages as shown in the second figure. See, in the second figure that shows, so current and voltages are not proportional to each other. In devices such as a semiconductor diodes, the relationship between current and voltage which depends on the sign of V as shown in the figure. See, so the negative or it may be in the positive. Sometimes it shows in the positive axis, sometimes it is shown in the negative axis. So from this, the Ohm's law is not holds good. And the certain materials such as gallium arsenic used in a light emitting diodes like LEDs, the relation between V and I, so not a unique as shown in the figure. The relationship between V and I is not unique as shown in the figure. So then there are more than one values of V for a same current in the as shown in the figure. See, so for a same current, for example, you can consider this value. You can consider this value at particular this current, there are more than one value obtained. See, so at this particular current, this is a 1 voltage, and this is the second voltage, and this is the third voltage. There are three different voltages are obtained for a particular one current value for the same current. So we'll get the three different voltages. This is obtained in the third curve, and this does not obey the Ohm's law. So there are some limitations of Ohm's law. And last one is the device that obeys the Ohm's law are known as ohmic devices. The resistivity of various materials. See, the materials are classified as a conductors, semiconductors, and insulators. This is the basic thing. And this classification is based on their resistivities values. In an increasing order of their values, the first one is metals or conductors. The metals or conductors have very low resistivities in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. One thing. Then second one is the semiconductors. Example like a carbon, silicon, germanium, like that. So have their resistivities values in the range 10 to the power minus 5 ohm meter to 10 to the power plus 4 ohm meter. See here, the resistivity value is average. But in case of conductor or metal, the resistivity is very low. That is in the order of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. But in semiconductors, its value is 10 to the power minus 5 ohm meter to 10 to the power plus 4 ohm meter. See, in the insulators, what happens? Insulators means like example like pure water, glass, rubber, ceramic, and plastic, like that. So I have resistivities values in the range of 10 to the power plus 5 ohm meter to 10 to the power 16 ohm meter. See, 10 to the power 5 to 10 to the power 16 ohm meter. That is the highest value. So that is the highest resistance in the case of insulators. See, the resistivities of materials depend on the temperature. In the case of semiconductors, the resistivity is also affected by the presence of a small amount of impurities. The resistivity can vary in as like it depend on impurities in case of semiconductors. The materials whose resistivity have a very small dependence on the temperature are used to make the resistors. Then now we want to discuss the concept of resistors. See, the commercially produced resistors are mainly two types, in which one is wire bound resistor. See, as mentioned here, one is wire bound resistor, another one is carbon resistor. See, wire bound resistor is like this as shown in the figure. The wire bound resistors are made by the winding the wires of an alloy. See, the first, that is, there is a metal core, around that there is a alloy wire is wounded. Like alloy means manganese, constantan, nichrome, like that. The choice of these materials is based on the fact that their resistivities are relatively sensitive to the temperature. The temperature coefficient value resistance, the temperature coefficient of resistance is very small. Then these resistors, actually these resistances are typically in the range of a fraction of an ohm to a 500 ohms. This is about the wire wound resistors. The next one is a carbon resistor. See, the resistors of a higher range are made mostly from the carbon. The carbon resistors, see, the carbon resistors are compact. So these are the compact one. So inexpensive. So this is very cheap, and therefore they are find extensive use in the electric circuit. Nowadays almost electric circuit, in the electric circuits there are use of these carbon resistors only. Since the carbon resistors are very small in size, their values are given in the, actually that their values are given in the color code system. See, so this is the carbon resistors. Its value which is given like a color code, given in the color code. How? The color code of a carbon resistor is like this. See, so for example, there is a given a color code like this: brown, violet, black, gold. See, so there is a given color code. Actually, this is the carbon resistor. On the carbon resistor, its value is given. That is in terms of color code. The first one is brown, violet, black, last one is gold. See, in the figure, the first two rings from the end give the first two significant figures. See, the first two colors are given here, which are brown and violet. The first two colors that gives the two significant figures of a resistance in ohms. Then the third ring, see here, the first two colors that shows the significant figures in the resistance in ohm, and the third color, there is a black color here. This is an example, just an example. Black, violet, brown, gold, like this is an example. So here, according to example, I'm explaining now. The first two rings that shows the two significant figures of the resistance in ohm. Then third ring that indicates the decimal multiplier, the third color that shows the decimal multiplier. The last color that shows the last ring that indicates the tolerance in percent about the indicated values. The last color that shows the tolerance. See, the last color indicates the tolerance in percent. One example is given here. That is like AB into 10 to the power C plus or minus D percent ohms. A and B that shows, that is significant figures, two significant figures, A and B. A is one significant figure, B is another significant figure. And the third ring that indicates, so that is the decimal multiplier. The decimal multiplier that is in terms of 10 to the power C. Then D, plus or minus D, that represents the, see, that represents the tolerance. That is in terms, so totally it is in terms of ohms, because it is the value of resistance. The SI unit of resistance is ohm. See, there is a one table is given here. So you need to keep it in mind. According to this table, you need to see its value of the resistance according to color code. See, so there is a letter is given here: BB, ROY, GB, VGW. See, there is a letters here given. B means black, so its number is 0. Next, again one more B, that is a brown, number 1. R means red, number 2, like that. So on is given 0, 1, 2, 3, 4, 5, 6. Then, so this is the color, the last ring color. There is a gold, silver, and no color, and it is about its tolerance. See, first two rings in the resistor that shows the significant figure of the resistance. First, you need to keep it in mind. According to the value of resistance can be calculated using color code of resistor. See, with the example I am explaining now. So this is the table here, in which the first column that gives the colors here: black, brown, red, orange, yellow, green, blue, violet, like this. And so according to the color code, there are two colors, first two colors that shows the significant figures like this. This is the first one and this is the second one. The third ring that indicates here, first two rings that indicates the significant figures, like first and second. The third ring, see here, this black ring, the third ring that indicates the multiplier, the decimal multiplier. Then fourth ring that indicates the tolerance of the given resistor. So according to that I am explaining now. So that is one example is given here. Now we want to calculate its resistance. See here, the first color is brown. See here, the first color, there are two B is given here, so don't be confused. So first color is brown. So first we need to take the first digit is brown. Brown is number 1 here, so that's why, sorry, brown number 1. The first digit is number 1 and I wrote here. Then second ring that shows the violet color. So the second significant figure, no, you need to see in the second column. In the second column you need to see the violet color. So for violet color, this is the value. So second significant figure value is 7. And third one is, see here, the third ring is black color. Third one is decimal multiplier, that's why multiplication symbol is here. Then so in the third multipliers column you need to search black color. So here this is the black color. Here this value is the multiplier value, 10 to the power 0. So 10 to the power 0. The last one is gold color. So gold color that you need to see in the tolerance column. Gold, so which has plus or minus 5%, plus or minus 5%. So this is the value of the resistance of this resistor. The resistance of the resistor can be calculated like this, or this value can be written as 17. 10 to the power 0 nothing but 1. 17 into 1 17, then 17 plus or minus 5%. This is the value of resistance of the above resistor that can be determined using this color code. This is one example. Then we'll go to next example. See, so there one more resistor is given. So now you can calculate the value of resistance. See, here there are 4 colors are given. 4 different colors are given. First one is green ring, red ring, blue ring, silver ring. The first two rings, see, the first two rings that shows significant figures. This and this, A and B. So first green color. So in the green color, the first significant figure is 5. Then second is a red ring. So in the second significant figure, you need to search red color. See, this is the red color, 52. Then third ring is blue color, that is a multiplier. See, the third ring that indicates the multiplier according to this rule. So the multiplier and into the third ring is blue color. Blue, so you need to search blue here. This is the blue color, that is equal to 10 to the power 6. Then plus or minus silver. See, search in the tolerance column. Last one is tolerance. In the tolerance, search that is equal to plus or minus 10%. So plus or minus 10%. This is the value of the given resistor of this resistor. The value of resistance of this resistor. So like this you need to calculate the value of resistor. So its value is given here, 52 into 10 to the power plus 6 plus or minus 10% ohm. The value it is in terms of ohm because it is the value of resistance. The next one more example is here. So you need to calculate. See. So in the So in the given color code, the first two rings that shows the significant figures A and B. Then third ring that shows multiplier. See, the fourth ring that shows tolerance. The first ring is, that is a brown color. Brown color. In the brown color, first significant figure is 1. So you need to write 1. Then second is violet color. So the second significant figure, you need to search the violet color, hence its value is 17. The next one is black color. So black, The third ring that shows a multiplier in the black color, so that is equal to 10 to the power 0. Then plus or minus. See, next one is, here there is no color is observed, that's why no color. See this into mark that shows no color. If it is no color, then its tolerance is plus or minus 20%. So its value is plus or minus 20%. So this is the value of resistance of the above resistor, that is determined using color code. See now, so this color is, that should be in the same order. So keep it in mind, these colors which are in the same order, that's why to remember this color, so you need to follow a simple trick. So it's just a tricky word according to this. So there is a word in English here, that is B.B. Roy of a Great Britain has a very good wife. See, B.B. Roy. See here. First brown, black, brown. B.B. and R.O.Y is here. Red, orange, yellow. Roy of Great, G is Great Britain. Very good, sorry, very good wife. So till you, so you have these words for just remembrance. This is one word to remember the color as per the cereal. So that's why it is a BB Roy. Black, brown, red, orange, yellow, green, green, blue, violet, then gray, last one is white. So this is the formula for remembering the sequence of the color code. BB, see here, BB, BB, ROY, Roy, Great Britain as very good wife. BB Roy of Great Britain as very good wife. This is the simplest formula to remember the sequence of the color code. So like this, you need to calculate the resistance of the given resistor. Thank you everyone.